With that, let's start the actual festivities. The speaker today is Yixin Wang. She's an assistant professor of statistics at the University of Michigan. She works in the fields of Bayesian statistics, machine learning, and causal inference. And I should say that one of the there's a direct quote from one of her colleagues that she's the up and coming person, absolutely brilliant person for causal inference studies. So with that, I should probably hand over. You should take it away.
Yeah, thank you. Thanks for the very kind introduction. And I'm excited to talk about this line of work we've been doing in this community. And I would really love to see if it may connect to astronomy and potentially looking for applications in that world. So the title of the talk is Harnessing Geometric Structures in Causal Representation Learning. But the broader goal of my talk today is to sort of introduce this task of causal representation learning, where sort of a subset of the causality and machine learning community has been working on this task for a couple of years with both theoretical and applications-wise study. And I'd love to see if it connects to a lot of the applications that you guys care about. So this is joint work with a series of people since my postdoc with my post-advisor, Mike Jordan, and then a bunch of collaborators from Mila, including Yasha Benjo and Kartik, and Diva and Amin were two students we're working with. All right, so I'll just jump right in. Well, actually, let me preface, there's a word causal in that. And a lot of it is because we were interested in interventional data, but broadly, this could all, whether there are parts of it that can, like parts of the method and the tools we will introduce will be independent of causal inference, and there are other parts that may be closer to that. So while we have the word causal in there, we can sort of, I think there's room to think more broadly about this task. All right, so I'll just get started with talking about a task that really motivated me working on it. So, I did my PhD at Columbia, so I lived in New York City for many years. And one thing I think a lot about when I lived in New York City is how do I merge lanes in New York City heavy traffic? So this is what merging lanes look like in New York City heavy traffic. And for what it's worth, I'm a terrible driver, so this is what I look like when I drive. So, this is the real thing. It's so difficult to merge lanes in New York City heavy traffic. So as a statistician, what do? I go try different things and run experiments. So I actually have tried many different tasks, strategies to do this. I've tried to rent different colors of the car, or try to put up a bumper sticker on the car to ask people, hey, let me merge. I really needed to. I'm a very nice person. I tried to put up some gestures so that people know I wanted to merge. At some point, I put a dog in my car to beg people I wanted to merge, or even put more dogs in there.
One quick comment.
Yes.
I'm glad that you make the gesture in New York City and not in London.
Oh.
Oh.
Yeah, thanks. Right, so yeah, I tried all of these things, and as a statistician, what do? We run all of these experiments and collect data points, right? For every single time, I rent a different make of the car with different car color, just whether I did a gesture, whether I have put down a bumper sticker, how many dogs I have, maybe measure the distance to the other car, whether I successfully merge or not, all that. So this is how we do causal inference classically. And of course, this is experiments. We have a lot of tools in classical causal inference for doing that. The thing with this is really expensive and takes a lot of effort, where I need to pay and rent a card and collect every single line at this table. But what's nice about this is the data, it sits in a table where we know how to do causal inference with all of these classical tools. So one day I realized this is too expensive. I was a grad student. This is too much. So I realized there is actually another source of data, which I could go online, look at the surveillance camera, and just learn from how other people merging lanes and whether they were successful or not. And so this is what I meant by sort of unstructured data, which broadly just thinking about it as images, video, text sometimes, and say molecule structure and all of that. Like this is so a lot of unstructured data that doesn't put in a table form, right? And what's nice about this is all the information I want to record here in an actual experiment is all present in this data. Like I could look at the car that's trying to merge, look at what the car make and car color and distance and all of that, and whether they were successfully merged or not. I have all of that information in the data. So all of that is observed if I were to record them. The thing is, how do I extract these factors from these high dimensional, potentially unstructured data so that I can down the road apply classical causal inference techniques?
Excuse me,
Yes.
could this may seem frivolous, but I don't think it is. What is an unsuccessful merge? How do you define that, and what are its characteristics?
A successful merge, we may look at the video and we may see people might try to merge and then didn't eventually get into the lane and then swap out. That will be recorded as an unsuccessful merge, right? But this is more of an example, if that makes sense.
But I'm just wondering if the line between successful and unsuccessful is a little bit fuzzy here.
Mm-hmm.
It's a matter of how long it takes you. Presumably, eventually, everybody successfully merges. It may take a long time, or they end up with a crumpled fender, but still, it's not a yes/no thing in some sense.
Right. Yeah. I think that makes a lot of sense. Which would mean instead of looking at the outcome, that's whether I have a successful merge, I may better put up this column as how long it took for me to merge. And that's still a causal inference problem where I wanted to understand what are the factors that will help me, for example, decrease the number of minutes or seconds I needed to merge. And thanks.
Can I follow up a little bit on that?
Yeah.
So the point that Jeff made about it not being a frivolous question, it is that if I think essentially it leads into some sort of a completeness issue, right, of the data. So in that same sense, so this is limited to, for instance, people who put the turn signal on before the merge, right?
Mm-hmm. Mm-hmm.
And I drive a lot in Boston, and people don't actually do that.
Mm-hmm.
And they still manage to merge. So what is, how it's, in a sense, there is a larger universe of the data than is being considered here, right? Does that have an effect?
Yeah. Okay. I think this is a great question. So we'll get to see more of it later on in how we actually do this, but I like this question about the completeness of the features we're going to extract. So later on, the algorithms as we do it, we'll ask ourselves to extract features so that we can reconstruct the original data, which means I will aim for a complete set of features that is present in the original image or video so that I can fully reconstruct the original data, if that makes sense. Yeah. So, but this is great. Yeah. That's not a frivolous question. Yeah, absolutely. Cool. So the goal, for us to be able to do causal inference on this type of information is we want to be able to extract the factors that's relevant and potentially the complete set of factors that's relevant and understand their causal relationships. And what I want to emphasize that here we work with a setting where everything, I assume all the factors is relevant, is observed in here. So I know there are classical challenges in causal inference with observational data with potentially unobserved confounders and all of that. None of our method is going to be able to get around that, nothing. That fundamental challenge of causal inference stays. What we are trying to work on here is if we were able to do classical causal inference with all the factors actually observed, It's just here, these factors are not presented in a way that everything is organized and nicely labeled in a table, but rather presented in this form of unstructured data, and we need to extract that. And what we're going to work on is how do we extract all of these features from this image or these unstructured data in general. All right. So the goal for us to be able to take all of this type of images and down to this table so that we can down the road do causal inference is what we call causal representation learning. Broadly, we want to extract latent factors from these images. So you can think about, this is closely related to all of the classical work of latent factor modeling and representation learning or dimensionality reduction. We'll talk more about how this particular task could be different, but that's closely related. So all we need to do is to take all of this images and do dimensionality reduction and identify these features as relevant in these images. And down the road, we're going to apply classical causal inference to do that. So this task of taking these unstructured data and convert them into this table is what we call causal representation learning. All right. So this is the setup. I want to go into a little bit sort of more detail and be more concrete about what do we claim as a success of causal representation learning and what's causal about it, and what the vision of this community had in terms of causal representation learning. So causal representation learning is an unsupervised task. Was there a question?
Yeah, sorry to interrupt, but could you just define a little bit more what you mean by latent variables and also even unstructured? When you say this data is unstructured, what exactly do you mean, and what do you mean by latent?
Yeah. Okay, great. So by unstructured, I just mean data that needs tokenization and needs some form of representation learning. So like broadly think about it as like images, video, text, molecule structure. Yeah, sometimes people think gene expressions are that, but not exactly so. So sort of in particular, I could force myself to write down these images put them into a table, but then each column of the table will be a pixel value of the image. And that variable is not meaningful for us to do causal inference. We need some form of conversion of that image down to some meaningful variables so that we can do causal inference. So that type of data that needs this conversion, we call it unstructured. Well, I call it unstructured data in the context of this talk.
Great.
Yeah. And by latent, I don't mean, so I just mean that these are factors that live in this image. I needed to identify what they are. I mean, they are extractable from this image. They're not like genuinely unobserved variables. They're observed in this image. It's just oftentimes we'll fit a latent variable model as a tool to do dimensionality reduction and look at what these latent variables mean. And these latent variables will be, we extracted will be these features we'll look at, if that makes sense.
Got it. And it's a choice you make when you're structuring the data as to what you think are the latent.
Right, exactly. Yeah, precisely. We will get to that. And I mean, there are particular tasks and what we want to extract, these are all so design choices that go into the thinking, the eventual goal of causal representation learning. Yeah.
Great, thank you.
Cool. So I want to go into a bit more detail, as in what do we mean by causal here, and why do we want this type of factors here? How is it different from classical latent variable modeling? And what does it mean to be success or failure in the context of causal representation learning? Like, what do we want to get out of causal representation learning? So the starting example we can think of is causal representation learning is an unsupervised task. So we don't have labels at all. And the goal is to just take these unsupervised data and identify independently controllable latent factors. And this independently controllable factors are what we mean by causal here. So this is sort of different from, I mean, this is particular in this context, how causality is meaningful. And I mean, these will be factors that we'll potentially see interventions on by some other people. This is still vague. I'm going to give an example of that. So the canonical task we can think of is I could look at a data set of unlabeled car images. I just extract all of these cars from these images I look at. And the goal of causal representation learning on the set of unlabeled car images is I want to extract some latent factors or like obtain some low dimensional representation of this high dimensional image in a way that every single dimension of my representation corresponds to a hopefully semantically meaningful and importantly, independently controllable factor. So a success example will be if I, for example, obtain a three-dimensional representation where the first dimension corresponds to car make, the second dimension corresponds to car color, the third dimension corresponds to window tint, like every single dimension corresponds to something different, semantically meaningful factor, we claim that's a success. And this is independently controllable in the sense that I can hold the car make fixed and change the color of the car, and that's still a valid car. I can hold car color fixed and change a car make or change a window tint however I want it, and that's still a valid car. That's what we mean by independently controllable, right? That doesn't mean that these factors are statistically independent. They may well be correlated. This is just these factors, I can hold one fixed and however change the value of all the others and they're still valid, if that makes sense. So these are a pair of examples where one is a successful representation we got from causal representation learning and the other is failure. Or if I get this two-dimensional representation where the first dimension is car make and second dimension is car color, then this is great. I identify independently controllable causal factors. If I get the same two-dimensional representation that contains same amount of information, where the first dimension is the sum of the car make and car color, and the second dimension is the difference between car make and car color, that's failure for us.
Can I ask a
in the sense that every single dimension kind of mix up two semantically meaningful factors. Yeah, is there a question?
So how can you tell? I don't know if you'll talk about this next or something.
Yeah. I will talk about that next.
Okay, all right.
The absence.
My question.
Yeah. This is great. So, right on the outset, we don't have access to these actual labels, so we kind of need to tell by formalizing these like what do we mean by independent controllable, and yeah, we'll talk about that. One thing I really want to convey through this success and failure example is the set of methods we consider actually more focused on how do we organize the information in this in representation learning. So I mean, we'll still use some other dimensionality reduction tools to make sure to control what information we want to put into representation learning. And what causal representation learning does is, given we know what is the set of information we want to put into representation, how do I organize them across different dimensions? Right? I mean, this pair of representations both contain exact same amount of information. We want to go further than that by organize them in different dimensions in a good way, so that that's amenable for downstream causal understanding or learning the causal graphs and so on and so forth. All right, so this is really about how do we organize this information in different dimensions and identify these factors. So this is actually also called disentangled representation learning in the machine learning community, where we consider this is a disentangled representation and this one is not. This is entangled representation. So people might ask, why do I care about this? Now that if we're able to put different semantically meaningful factors in different dimensions, that we can consider mix and match. Now, I think causal representation learning sort of goes beyond disentangled representation learning in the following way, where we could have latent causal factors, or these latent factors are semantically meaningful, and they may be causally connected. So this is an example where I can have some unlabeled car images. Here, every single image have 2 cars, and I have a white car that is chasing a blue car, and we can pretend, we can suppose that the causal, the location of the white car is going to causally affect the blue car. Treat that as an assumption. I know we can tell the story the other way around, but we have this white car that's chasing the blue car, and we have this causal, we could have this causal relationship between the white car and the blue car. So the goal of here, still doing causal representation learning, is to take these images and identify that I will have 4 latent factors, each being the XY coordinate of the white car and XY coordinate of the blue car. And so I have 4 factors, which are really driving the differences across these images. And these factors are causally connected, in the sense that if the location of the white car is having a causal effect on the blue cars, then XY coordinates of the white car is going to have causal arrows that go into the XY coordinates of blue car. So how this is different from the car example we had is here in my image, I assume that these factors, these disentangled factors, don't causally affect each other, but causal representation learning can go further than that by saying we will also want to be able to handle cases where these latent causal factors are causally connected. Of course, this is a much harder task, which will need other types of data for us to be able to identify that, but this is sort of the vision people had. People have also worked with sort of more toy physical system, where this is these are images of a two-ball system where the green ball and red ball are interacting with each other. So potentially the green ball may have a repulsive force on the blue ball, on the red ball if it's an upper quadrant, and the green ball may have an attractive force on the red ball if they're in the lower quadrant. Then again, it's a similar situation that we want to just take these images, which are snapshots of that two-ball system, and identify that there are 4 latent factors, with each of them being XY coordinates of the red ball, XY coordinates of the green ball, and they're causally connected. In the sense that the XY coordinates of the red ball will have a causal effect on the XY coordinates of the green ball. So the success of this causal representation learning task will be taking all of these images and then identify these latent factors and understand their latent causal connections. And this actually being done a lot of biologists are really interested in that when they have a lot of observed features for them are gene expressions, and they look at phenotypes, which are like whether people have disease or not, and they wanted to understand what are the causal mechanisms on these gene expressions, on these disease status, and they posit that they're all driven by some latent factors, which also may be causally connected among each other, that drives both the phenotypes, the disease status we look at, and also the gene expression. So we want to identify them along with their causal connections.
Excuse me, sorry, could you back up to the previous slide? When you were talking about this, the car analogy, and point out that they're, in some sense, they're both causing each other.
Mm-hmm.
It me that there's sort of a qualitative difference between 2 cases. If they're both affecting each other, there's no causal arrow.
Right. Yeah.
Like A causing B and B causing A, it's really something qualitatively different. A and B are mutually dependent, or some other word.
Right.
Is it possible to formalize that distinction?
Yeah. So I think what we're talking about is, what if I may also have maybe working with a cyclic causal graph? So the white car can be causing blue car, and the blue car may also be causing white car. So for all of our work, we require the causal connections among these latent factors to be acyclic. However, if we have time series data, like if we record this over time and we enroll this causal relationship over time, then even though white car and blue car can be mutually causing each other, we can enroll them to still be acyclic, and we will be able to handle that if we have time series data. I think at the very end of the talk, I'll show one time series example we're able to do. Yeah.
Okay, I'm not. I mean, I'm thinking of the moon going around the Earth and so on. The moon and the Earth are affecting each other, and it's one causing the other. That's very different from causality, even a two-way causality. Anyway, I think what you're saying, but it's not completely clear to me that you can formally distinguish mutual effect from bidirectional causality.
Okay. Yeah. So I think, well, just from observational data, we cannot. The only case and the way we understand causality here through these connections is to consider what happened if I perform an intervention to change the location of the white car. How is that going to causally affect the location of the blue car at the immediate next time step? And of course, that location, the blue car, will come back to causally affect my the location of my white car, and they have a mutual have a mutual effect on each other. So if the effect is, so if we have instantaneous measurements over time, like continuous time measurements over time, and we assume that any causal effect, any causal relationship will have to be from t-1, from t to t plus epsilon, like will have to show up at the next time step, then we can distinguish that. If we only have, for example, measurement at equilibrium, or like look at the steady state, we will not be able to. And if we only have observational data, we may not be able to. That makes sense.
Right, yeah, but of course, I'm sure you're aware that astronomers don't have the luxury of being able to manipulate and intervene and get physical causality. But
I'm not sure we do in traffic either.
Right. But I think, I think the intervention we talk about is kind of in a broader sense there. And if we have some form of like measurements over time, and we don't just have things like at steady state, there may still be chances to be able to handle that. But yeah, and this is a really,
I guess we need to give us eventually a definition of what you mean by causation. That's, I guess, why this is.
Yeah, exactly. Yes. I mean, in these image cases, we consider these causal factors or things we can intervene on, and we'll see an effect. So these will be factors that we'll see interventions on. But yeah, we'll talk more about that in the rest of the talk. Yeah. Cool. So yeah, so the goal, I mean, this actually shows up a lot in biology, where people identify these latent factors, as in they consider, for example, gene programs, and they'll say, I want to identify these latent factors by performing causal representation learning algorithms. They will take it to our collaborator to interpret what these causal factors are. And the goal really down the road, what's causal about it, is we want to design effective interventions on these latent causal factors so that we can achieve, for example, a particular biology process, or want to cure disease, or want to improve the disease condition, so on and so forth. So what's causal about things here is we identify these factors. We want to be able to design interventions on them so that we can achieve a desired outcome. Even if we may not be able to think about, like, perform actual interventions, people want to be able to think about hypothetical interventions and that. So, I mean, this is a broader vision of this whole community of causal representation learning. And I think we're not all the way there. I mean, there's some work in progress trying to push toward the end. I think what I'm going to focus on in this talk is just the first step. How do we do causal representation learning? So, I mean, I think by just the description of this task, it looks really much like identifying latent factors, right? So why can't we just go ahead and fit a very flexible latent variable model, which is something we're really good at. So we could do that. We can go back to this car example, fit our favorite nonlinear factor model, or linear factor model, or a very flexible one. And we can always obtain what we want as a representation function. Here I write down one example of a nonlinear factor model, which we call.
That just looks like nonlinear regression. What's the factor here?
Oh, the Z is latent. So this is factors. So I'm saying my high dimensional data. This
Z
image,
is not observed. Z
right,
is not
Z
observed.
is latent here. Yeah.
Not observed.
Right, is not observed.
That's not a function of the data or the X's or the figures or images or anything else.
No, they're not observed. Like I'm just assuming my images. So X is my pixels of image.
Yeah.
And I'm saying all of this pixels of image, this is the whole vector of the pixel of the image. They are generated by some low dimensional latent factors through some nonlinear transformations. And I say my pixels follows the Gaussian distribution.
So just to clarify, so that this car make, car color, and tint, etc., they are the Fs or the Zs?
They're the Zs.
The Zs, okay.
The Zs.
But you observe
So,
those.
because for every single image, they are generated by a particular value the car made, particular value the car color, particular value the window tint, which is the value of the Zs. That makes sense.
I'm sorry, you can't see the cars.
We can't see the cars, but I can see the image of the car. So this X is the.
How is it that you don't know the make, the color, and the tint?
Sorry, can you repeat your question?
How is it that you don't know the make, the color, and the tint if you can see the car?
The thing is, we don't know what these latent variables necessarily are. I'm just giving an example.
That's a different thing.
Right.
That's a different. That doesn't. You can have a high dimensional data set and you don't know which variables or which functions the variables to include. That doesn't make them latent variables.
Mm-hmm.
Latent variables are unobserved.
Right. So I guess here we can think about it as the low dimensional representations of the image. I can extract, so these are variables I can extract from these high dimensional image.
Yeah, so that's saying that X and F are exactly the same, but F is unknown.
Right, F is unknown, and Z is also unknown.
Z is not a function of X. You cannot compute it from X. A moment ago, you said it was things like the color and car make, right? If you have the image, you can see what they are. You don't know what you're looking for. That is to say, you don't know F.
Yeah,
you don't
exactly,
know
exactly.
I think of the image.
Right,
But you know the image.
Right, exactly.
So X and Z are the same.
Right, so yeah, Z is a summarization of X so that we can reconstruct X.
If you want, you can say F of G of X, and you don't know F or G, but that's actually the same thing as saying F is, F or F of G, it's the same thing. It's just a different level of function.
Right. Yeah, I think you're right. Yeah. So I mean, that reconstruction is precisely what we're later on going to look at. So
I wonder, this is Xiaoli, Yixin, that I wonder if there's is it possible there's a language barrier here? David, that if you think about, if I'm thinking like a machine learning person, the image is just bunch of pixel values, right? I don't see any color. I don't see it's just bunch of values. If you treat it the very, kind of a contextual free, that's just a bunch of pixel values. And I want to see in these pixel values what kind of thing represent the color, what kind of maker. Right. Maybe that's the way they're thinking about calling the latent. It's
right, exactly. Yeah.
Maybe latent for laziness, right? Because you're not looking at particular. Is that possible interpretation? Why we use this?
Yeah, I mean, that's exactly what I meant. Like in statistics, this is just a nonlinear version of probabilistic PCA. Like this is all we're doing. So I understand the word latent can be confusing. It's sometimes confusing to causal folks too. Like, what do we mean by something that's truly unobserved? Here, this is a dimensionality reduction algorithm. Just the way we map the high dimensional data down to some low dimensional variables. This could potentially be nonlinear, but really all of these features are in the data, and we just don't know what we're looking for. Yeah.
It is also true. Sorry if I may. It is also true in machine learning that these latent variables, which are whatever compressed representations from the high dimensionality data, are also not observed. But I think a big thing, something that people are trying to do that is probably related to the story you're trying to tell us is, yes, we know we don't observe them. We know we can generate the data again from that compressed version, but can we link each of those latents to something that is physically meaningful to us, right, or interpretable? So it has to do with interpretability, right, as well. Can we make that latent space or bottleneck space, if you want to call it, interpretable by trying to link it to specific quantities? I think that's part of what. Yeah.
This is exactly.
Okay, that actually makes good sense. But David, I wonder, the key issue is that I think the words observed, I guess they are, we think about observed is observable to human, but I think machine learning people may think about observable in the sense, can the algorithm itself detect what those things are when you're given a bunch of this, just the pixel values, right? So the meaning of latent, could mean different things, depends on who is the observer.
Can I interject for a moment? I mean, I think this is similar to the Lira boundary thing that we're trying to do. So for instance, we got all these pixels with intensity values, but we don't know where the actual source exists. And effectively, the sources and the boundary of the source would be something that we can see as humans, but needs to be told to the computer. So that would make it latent, maybe, from a machine learning perspective.
Yeah. I mean, that's exactly what I meant. They're just things
closer to this example here, right?
Yeah.
Like latent variable would be something like, I don't know, the power of the engine, for example, which might have some causal relationship to what you're observing, like the probability, for example, of merging.
Yeah.
But it's not something that you can directly extract from the image.
Or the age of the driver for a statistician would be latent. Yeah. Something that's not, you can't compute it from the image.
Right.
If the image is very blurry, you might not be able to compute the make,
Right.
It is interesting. These terms do I think different views take a different meaning but mean something. I think probably it will be safer to say you're looking for the low dimensional kind of a feature.
Yeah. I'm looking for a low dimensional feature. I want to extract them. I want them to be able to reconstruct my data. This is all I'm after. Yeah.
Dimension reduction.
Yeah.
Dimension reduction.
Yeah. This is precisely dimensional reduction. Just nonlinear dimensional reduction. This is all of it. Yeah. I just want to, after we've done this dimensional reduction, I want every single dimension to hopefully mean something, and to see if there are ways we can nudge that dimensional reduction to hopefully mean something. That makes sense. Yeah. So, but thanks all. Yeah, this is really important clarification. I think the word latent, the word unobserved is very confusing in a different context. Right, but really all we needed here, all I'm saying here is I have some algorithms. So I can do dimensionality reduction, think PCA, nonlinear ICA, like type of stuff. So that I can get some estimate of these representation, which is a Z, which is a deterministic function of my data. And this is what I want to learn. Like the goal of representational learning is to learn this G function that I can map my high dimensional data, potential and structured, down to some low dimensional features. This is all I'm after. Now, the issue with nonlinear dimensional reduction is identifiability is a big issue. And I mean, identifiability is classical topic, but it bears practical consequences in here, which I'm going to talk more about. So the particular identifiability issue, if I just run the same algorithm twice, I could get at 2 different representations that can reconstruct my data equally well, and like the same model. I just have multiple valid answers. Now, I mean, this is a classical issue. It really bears consequences in this particular task, because from the causal story people were after, first, I need to be able to take these factors to my collaborators, to the biologists, for example, we work with, to understand what they are. So if I can't even lock down one representation that they need to interpret, I couldn't do that. Moreover, we kind of told the story that we want to also understand the causal relationships between these latent factors, which is a causal graph. And if I couldn't identify what these latent variables are, then it really doesn't make sense for us to talk about the causal relationships or the causal graph among them, in the sense that, I mean, the causal graph among xi3 and xi2 will be completely different from if I have the two-dimensional representation to be in the sum and the difference. So if we want down the road really arrive at a meaningful causal graph that we can in some form talk about, we really need to be able to identify these identify these features in a way that they're separate out in different dimensions, like to be able to get to xi3 and xi2. And also what's important is for biologists, for example, they really needed to, down the road, design targeted interventions. We need to intervene a particular factor or intervene a particular feature. So if we couldn't even identify what that feature is, then we couldn't do anything about that. So while identifiability is a classical topic, there's particular identifiability we're after here, as in we want to be able to separate out these different features in different dimensions so that we can meaningfully talk about their causal relationships and potentially talk about their interventions after interpretation, of course. So, and I want to also take this opportunity to talk about what do we mean by identifiability here, which is slightly stronger than what we usually talk about, in the sense that to be able to identify these features, we'll say that my data is generated by some ground truth features we're after, and it's mapping from the latent, mapping from the low dimensional feature to the observed spaces through this what we call mixing function G. And we want for an algorithm to be able to identify these features is I want to have an algorithm that can take my data X and output a G hat, which is an estimate. It's going to coincide with what G is. And also, I'm also need to be able to identify the features so that they will exactly correspond to the true data generating features in the data. Right? So I want identifiability of both G and Z for every single data point. Right. So at this point, we naturally ask, this really just look like nonlinear ICA or a lot of the other dimensionality reduction methods. Why can't we just go ahead and use that? And there are a lot of studies about how to identify these features, low dimensional features, or just identify these transformations of high dimensional data from identify these features from high-dimensional data. And the difficulty with using all these existing results is most of the methods require all of these latent features, in particular, they call it latent factors, but they're basically like separate features. They need things to be statistically independent. They could come in ICA, come in some modern literature of nonlinear, like latent variable model, potentially with some other auxiliary variable. We always require all of these features to be statistically independent. But even an example we look at just now, the features we're after are often not statistically independent, like the car make and car color. They may well be correlated. Even in these other examples, we're interested in the causal graph among them. They're causally connected, so they cannot possibly be statistically independent. So now the question is, when these features are no longer statistically independent, is there anything we can do, and how can we do that? So what assumptions beyond statistical independence, which doesn't hold from the outset, can help us identify these features that are correlated, potentially causally connected? And the tools we're going to use is we call geometric signatures. In particular, we're going to look at the support of the features and look at the shape of the support features. And this whole thing actually starts from just empirical observation. So, we have all of this image data in the UCI repository, and humans had actually hand labeled what are the meaningful features that live in these image data. So for example, there'd be image data sets of human faces, and people will hand label these features like hair color, skin color, whether this person is smiling, whether there are sunglasses on. Humans have hand labeled these features. So we're like, these are the features we want to extract from these high-dimensional images. Humans have done that. Let's go in and look at like what properties do these hand-labeled features have so that we can learn from it and take them to help us in other data sets to identify these features that may be meaningful. Right? So we actually going to look at lots of image data sets and in UCI repository with human hand annotation of these features. And we do the first thing that everyone will do, just make a scatter plot of these features. And this is what we found. So in a lot of the cases, especially in large data sets, we find that even though these features may be statistically correlated, if we plot their support, they satisfy what we call the independent support condition, which means here is an example of looking at two features. People have hand label, one is orientation, the other is a scale. If I change the value of one of the feature, the support of the other feature does not change. Now the distribution may still change, they may be correlated, but if I change the value of the scale, the support of orientation is always covered this whole space. So on the left column, these are examples of features that satisfy what we call this independent support condition, which we eyeballed, and a lot of the features people have hand labeled satisfy this condition. Now on the right column, these are examples where they don't satisfy this independent support condition. For example, if you look at the bottom right, as we change the value of what we call entangle 2 feature, the support, which is the possible values that entangle 3 can take, will change, right? When entangle 2 take very small values, entangle 3 also it's only possible for it to take very small values. However, if we move toward the right, then the possible values that entangle 3 can take will largely change. And this is a violation of the independent support condition.
Question?
Yes.
So what's the data set that you're looking at in this case? What's the context?
Oh, yeah, so this is the context of we call 3D images. So there are 3D images of just objects, like you can see there may be cylinders and balls and with different shades and different color. And so they'll talk about what is the scale of, for example, the ball and the orientation of the cylinder, that type of
Okay,
stuff.
so it's sort of what you might encounter in games, video games, that sort of
Yeah,
thing.
yeah, exactly.
Okay.
Yeah.
Right.
Yeah. So, I mean, this is purely empirical observation. We look at all of these data sets and we found that they all satisfy this. So give it a name of independent support condition. Yes.
Sorry, there are two things on this slide. There's independence and then there's correlation. Are you measuring true independence, or are you using correlation functions as a surrogate for dependence?
Oh, I'm using correlation as a surrogate function for dependence. I just meant to say they are not statistically independent. They may not be statistically independent, even if they could satisfy the independent support condition.
Okay, but what's they're not independent, but they're also not uncorrelated. Is that what's on here? They're correlated and non-independent.
I mean, I guess, right here.
I mean, sorry, what I'm trying to get at is in principle, you could stick with independence and try to measure independence, rather than the weaker condition of correlation.
Yeah. I guess this is the confusing illustration. I guess it would be better if I write down, for example, mutual information here.
Right.
And what we're after really is independence.
You're using independent in the English sense of the word, not in the statistical sense. You're just saying that the support is the cross product of the independent.
Yeah, exactly. Yes. And I wanted to distinguish this independent support from statistical independence.
Don't use the word independent, I would say.
Right. Yeah.
I guess I'm having a little trouble understanding this concept of support. Can you give a trivial example? I guess I'm still waking up here in California, but what is the meaning of the fact that the supports are don't overlap, I guess is a way of saying it.
They're not necessarily saying support don't overlap, but rather, okay, here's a way to think about it. So statistical independence means if A and B are statistically independent, then P of A given B is equal to P of A, right? That's the
property, but
right. So the support independence can exactly be written in this form by saying, instead of P of A given B is equal to P of A, I would say that support of A given B is equal to support of A.
Well, the possible values of one variable do not depend on the values of another.
Yeah.
So if you have a Toyota or a Honda, and Toyotas are not available in blue, but Hondas are, it's this sort of stuff.
Right. Exactly. Yes.
Oh, okay. So, all right. I think I can figure that out. All right. Sorry to interrupt. Thanks.
No. Great. Thanks. Yeah. I mean, this is exactly it. Like, I want all factors to be, all combinations of all features are possible. Precisely. So this is all empirical observation. So the thing with the, first I want to connect it back to the sort of the causal story, or the causal graph story, or the correlated factor story we're telling. It turns out there's a reason we kind of see this. I mean, it did tie into that. Well, we can show that with a very simple argument, under a positivity condition in causal inference, or sometimes understood as overlap condition, which could be a strong condition, but it's a standard condition in causal inference, we can show that the absence of causal connections among these factors, among these features, will imply that they must have independent support. Right. So it's sort of, they give us some reason to understand that there may be a reason why we see that empirically. But what's more important is we just take this constraint, as in I think we call that independent support score, even though I know this should avoid using the word independent. We just do the dumbest thing possible. Look at the Hausdorff distance between the support of these features and measure the Hausdorff distance between the support of the joint support of all of these features versus the product of the support. So imagine if they are really independent support, then they will have the Hausdorff distance supposed to be 0. And if it's bigger, then they're less so of independent support. We do the dumbest thing, and the way we estimate support is not robust. We just take Monte Carlo samples and do all the dumbest thing. And if we're going to do representation learning or dimensionality reduction, we put it as a regularizer. Surprisingly, it just worked. Where this is an example where we had a bunch of features extracted by arbitrary representation learning algorithm versus human hand-labeled features. And you can see that this independent support score, which is this Hausdorff distance, can nicely separate out these we call human hand-labeled features, which we call disentangled features here, versus arbitrary features spit out by vanilla representation learning algorithms. And I mean, this is just a contrast. This is different from statistical independence, where if we were to look at total correlation or Wasserstein dependency, so on and so forth, we will not be able to distinguish them. Whereas if we look at the support, we can nicely distinguish them. Moreover, if we
so a quick question about that. So you're assuming that the human labeled is in some sense optimal.
Right. Yeah, but that's target for us. Because human labels for us were semantically meaningful features that we can consider interventional. That's the whole thing we're trying to learn from.
Okay. Thanks.
Yeah. And so we also put it as a regularizer in these representation learning algorithms. It just quickly surpassed existing methods, where this is interventional robustness score, which measures the alignment of these unsupervised representation learning algorithm, the features extracted by these algorithms, with ground truth human labeled features. So we just pretend we don't have these labels, run representation learning algorithm, measure how well they align with human annotations. Just with this regularizer, we quickly significantly surpass what existing algorithms can do. And we found that this is precisely because of regularization. So if we just increase the regularization strength, we can see this alignment will go from around 0.5 to surpass 0.9, this cap of 1. So this is all just empirical. It turns out that among the data sets we were looking at, extracting these features and semantically meaningful features, this is really good inductive bias. We can make it.
Yixin,
Yes.
I have one comment, one question.
Yes.
One comment is that I understand that, basically what you're looking at is say, these independent support is actually a very weak version, right? Essentially is a hard constraint, saying if you have causals, if something gets removed, then there gotta be some relationship among them, right? So, but there's 2 questions. One comment is that you may want to distinguish between the theoretical, independent support or empirical independent support, because you could have some really rare combinations that you did not observe, which removed. It's still possible, right? You don't observe them. Number one. The more serious question is about your results. You must have some condition to eliminate the following possibility that there might be a circle, when A caused the B to remove something, but B caused C, and the C actually puts back something. So there got to be some conditions to avoid the thing. That's a very weak signal there, right?
Yeah. I mean, both are excellent questions. For one, you're absolutely right, and I mean, this is all just showing sort of empirical results. That issue you were talking about can totally happen. So instead of just, especially using empirical estimates of these Hausdorff distance, we actually can't just look at the support and look at the max or mean of every single features, but rather we oftentimes need to look at just 98% quantile or 1% quantile to get a little bit of nudge over that. But this is still very, like, there's a big gap between, there could be a gap between the empirical estimate of this and the theoretical version, the theoretical meaning of that. And that statistical property, we don't understand that well yet, because looking at the max and mean, it's a pretty hard estimate. To your second question, yes. So with all of these arguments we have here, we had to assume that the graph is faithful. So there doesn't exist this kind of cancellation you were talking about, where there are additional independence or conditional independence, or these cancellation independence or relationship that could exist beyond what we have in a graph. So that's what faithfulness conditions kind of show up in. If that makes sense.
Thank you.
Thanks. So this is all sort of empirical. We start with what humans have done and trying to figure out what things can get us there. Now, I made a big deal about we want to identify these latents. It kind of works in practice. Does it get us all the way to identify these features? So it turns out with conditions, of course, the answer could be yes. So for the rest of the talk, I'm going to talk about some of the results, and also just give some intuition of why this may help us sort of identify these features we wanted to extract. So the setup we're going to look at is the one we wrote down, where I say my data, these pixels and images generated from some low dimensional features through some mixing function G. So one of the first result we have is if we assume that G function, this mapping from the feature space to the observed space, is a polynomial function, we call it a decoder. And we look at all of our features are bounded. This is crucial for us because we're making use of support to identify these features. So if the support is infinite, there's nothing we can do about it. So we have to look at bounded support. Then what we can show is just pairwise independent support can help us identify, can provably identify these features up to coordinate-wise permutation, shifting, and scaling. So what this means is I am able to sort of separate out different features in different dimensions. Of course, they're permutation invariant. Within each dimension, I don't know what the scale is or the absolute value is, but I can separate them out in different dimensions. And with that, we can already meaningfully talk about causal relationship. Because we know every single variable up to shifting and scaling. So I want to be sort of this the only sort of technical result I show, but to formally say this, we assume that my data is equal. This is equal to some mixing function of some features, and the goal is to learn this extraction representation function applied to the data. We get this representation. What we exactly did is what one of the questions hinted at earlier. We solved for this reconstruction identity of we encode this representation, encode this data and decode it so that we can reconstruct, subject to the constraint that the latent, the features we extract satisfy this independent support constraint. Then just by these two, under the conditions I just said, where the G is a polynomial and my Z's, my features satisfy independent support, then it can identify these features up to permutation, shift, and scaling. The way we write it down is to say that the representation Z hat we get will be a transformation of the true feature, where this pi is a permutation matrix, lambda is a diagonal matrix, plus C, which is shifting. This is just stating it in math. So I wouldn't say it generalizes, but it's a parallel result for us to think about usual nonlinear ICA or linear ICA, independent component analysis, to this polynomial mixing. We can incorporate some nonlinearity, and we can handle correlated features, but with independent support. So we kind of go from statistical independence to potential, dependent dependent features, but with independent support. I also wanted to give a little bit of intuition so that we kind of get a sense of what the conditions do and how can we get there. At this stage, well, first of all, the polynomial assumption of this mapping from Z to X basically can already help us identify these features up to affine transformation. So, at this stage, there are many other tools that can do this. Our work was 2022. So like if we use very flexible neural networks, you can also get this type of linear identification just by solving this reconstruction equality. Now, what's interesting here is what independent support as a constraint can help us in terms of identification of these features. The reason it will give us these coordinate-wise identification is the following. So think about what independent support, I visualize them. It basically says to support my features should be kind of occupy rectangular space, right? This is independent support. Now think about what linear identification will give us. The hardest case to deal with in linear identification oftentimes is rotation invariance. Right? I have this linear transformation that can have rotation invariance. So the way this independent support constraint, which tells us rectangular support, works really well with helping us with this rotation invariance, is if we rotate a rectangle, this is no longer a rectangle. So this is how having this independent support constraint can help us further go from linear identification down to coordinate-wise identification so that I can separate out every single factor in different dimensions. So this is the high-level intuition of how the theory goes and like what is the role of this independent support condition kind of plays. Of course, there'll be many other constraints that can also give us this type of property. I think what's nice about independent support is we saw it empirically, and this is what happens with the human annotated features that was extracted.
Xin, can I ask a question? Yes. Yeah. Is this sensitive to getting the number of latent factors correct? Like if you have one too many dimensions and there's no way to make any rectangle with like an extra dimension, will this have trouble?
Yeah, we will need to know what the number of latent what the number of feature is. Empirically, well, I guess theoretically it is. The theory will break without that, because we really needed this reconstruction here. Now, empirically, what we oftentimes have done is to just specify more of them, and then enforce independent support up to some sparsity, like we'll allow some other dimension has no variance, then we could do that. So that's what we empirically have done. Yeah. Cool. So yeah, this is the geometric intuition. Now, this is all about we're trying to identify these disentangled features, which satisfy independent support. I want to come back to what if we want to identify these features that can potentially be causally connected? This is where just a single observational data set can no longer just do it for us. We needed multi-environment data where every single environment comes from some intervention. And the reason is the following. So when my features are not causally connected, then this is what we have been dealing with for the first half of the talk. But the case of all of these features are causally connected is what we'll want to deal with here. To go from causally connected, these features, down to causally unconnected features, this is actually precisely what interventions does. Interventions, by definition, is the act of removing the arrow, all the incoming edges or arrows in a graph. So if I were to intervene on this node in this graph, will mean I remove all of this, and remove all the incoming edges to that node. And the act of removing incoming edges kind of help me move closer to the setting of my my features and no longer causally connected. So with the additional interventional data, we can leverage this multi-environment, like every single environment come from some interventions. We'll be able to leverage that structure and similar independent support constraints for us to be able to identify these features, oftentimes with sufficiently many interventions. Sometimes, theoretically, sometimes we need more, depending on the conditions we're willing to make. And once we identify these features, we can just run standard causal discovery algorithm to identify their causal graph. So what I want to emphasize here is we don't need to know what latent factor is being intervened on. And we cannot possibly know. If we knew, then this task doesn't make sense at all. Like, what are the factors, what are the features that can potentially be intervened on and is meaningful, is not known in the first place. We just need to know from multi-environment data that some features were intervened on. And we'll still look at the geometric signatures, as in just look at the support and make use of that to identify features. So I'm not going to go into details of that, but we could look at, we have a series of results where we look at just observational data together with different types of interventional data with different level of assumptions on the mixing function, the mapping from the feature space to the image space. We can identify these features up to different equivalence class. And practically what we do, I'm a machine learning person that really care about whether things works, we again just put in constraints as regularizers, and we measure how many interventions we needed so that we can identify these features that align with a human hand notation. So in this 2 bars example, we're able to get to, with all of these like nonlinear complex functions, get to pretty decent alignment of these latent, with these features we identify, and good alignment with a human hand annotation. So this is in the 2 bars example, and we can run causal discovery down the road. So what happens up to now is I talk about how we can make use of interventional data and to help us identify these features. And what's important here is we have one fixed causal graph, and it needs to be a DAG, so it will be acyclic for the entire observational data, which may or may not apply to complex multi-domain data sets. So here's an example where it often fails. So in the image data we may analyze, I may have one image where the cat is chasing the dog, and in here the dog is chasing the cat. So the causal arrow can go both ways. And I mean, there's no longer a fixed causal graph. So we also have developed other tools for us to be able to identify features when that could happen. I mean, of course, we'll get weaker results from there. And the principle we're going to make use of is still looking at potentially geometric signatures, but look at the invariance principle. And it's a weaker invariance principle in the sense that we'll ask the distributional properties of a subset of the features is invariant across domains. So instead of asking all the features and the relationships to be invariant across domains, we're going to try to figure out there's a subset of them that's invariant across domains. And what we can achieve is much weaker identification, of course. We'll say we can only separate out what is a set of stable invariant features and what is a set of unstable non-invariant features. And this also applied to cases where if I have interventional data that I intervene on multiple nodes at the same time, and I don't know what they are, I only know that multiple variables in these scenarios are intervened on. This also applies to that setting. So again, I'm not going to be able to go into details of that, but we have some results where we go out of a fixed causal graph and still able to separate out some of the latents so that we can help with understanding what the features there is. And the way to do that is also just put in like penalty, really simple. Take favorite representation learning algorithm and putting a penalty. Again, we can do pretty well with ball images, MNIST. This is handwritten digit images with variations. And with 16 domains, we were able to get to pretty good alignment of the human annotated ground truth features. And yeah, so there's some empirical results in there. So the last example I'm going to talk about is when we have time series data, we're actually able to do the same thing. We analyze video, where it's a video of salsa dancing sequence, where people is going to switch pose over time. So we're able to identify like different states as they switch in between, and we find out we can interpret post hoc with these states that they correspond to different dancing poses in the time series data, which we may or may not always have access to. So I think this is sort of all I prepped, and kind of talk about this task of causal representation learning, where there's a subcommunity in causality and machine learning people have worked on. The goal really is to identify these features that are semantically meaningful, and we really learn a lot from human annotations and trying to understand what inductive bias can get us there. And importantly, we consider all of unsupervised observational, potentially interventional multi-domain data, where we work with these features that are potentially correlated or causally connected, and we made use of geometric signatures by looking at the support. And we achieved some empirical success. So I think with that, I'll close my talk. This is a series of papers we've done sort of on this topic.
Thanks. Thank you, Yixin. That's a very, very interesting talk, and we managed to finish almost on time. Congratulations, I suppose. So are there any questions? I know there are plenty of questions, but before I hand it over to the people who want to ask the questions, I had a quick organizational issue. One of the things I think we wanted to do was discuss possible astronomical applications. We have no time to do that. So we should probably ask you back at some other time if we can deal with that in detail.
Absolutely. Yeah.
Okay. All right. So I'll then hand it over to people for questions.
Question from here and also online.
Yeah, go ahead.
Anyone? Yes, just shout. Okay.
So yeah, thank you very much for the talk. So you said you are focusing on the causal representation learning in this talk, but I'm curious about how to do the interpretation of the learned representation or learned low dimensional feature. Could you speak a little bit about this interpretation, the second part?
Yeah. So I mean, the way we handle these images is I just use this as an example. We look at different values of the latent. So here, this is a discrete latent variable where we have different states they're switching between, and we look at what are the images or measurements that map to different values of the same latent and eyeball what their feature is. I mean, here, especially when this one is discrete, it was pretty easy to kind of interpret, where we just look at these images, and when we're in the middle state, we'll have all of this like a different pose, different dancing pose. So in general, we'll also be looking at just different images that map to the same latent value and look at what features they have and contrast them with other with other feature with other images that has different value on that feature. If that makes sense. So for every single feature, we look at what images correspond to this feature equal to negative values, and what images correspond to this feature, look at taking positive values and see how they're different and kind of interpret based on that. That makes sense.
I have a question about this time series analysis when you mentioned. So is it, so do you rely on this being a gridded time series, or can we have events and it'll still, and the entire machinery will still work?
Like point process data.
Yes. Yeah.
Potentially, we've never tried on point process data, but I mean, here this is switching dynamical systems, so you can imagine like an event happens, some switches on, and if we have, we can do sort of latent. We assume, for example, there's a latent name and Scott process, well, latent Poisson process where events happen, and that can excite some of the observed events. We could do that. Yeah.
All right. Any other questions? If not, I guess, you know, we are hit the 1:30 mark, and we started to lose people. So thank you everyone for joining, and thank you, Yixin, for a very interesting talk. And I guess we'll try and get Yang to figure out another time so we can come back and we can actually discuss things in more detail, applications perhaps.
Yeah, absolutely. Great. Thank you.
All right. Okay.
Great. Thank you, Yixin.
Thank you.
Thank you very much.